Welcome to Spaceverse, your portal to cosmic adventures. NASA's twin Voyager spacecraft, launched in 1977, captivated the world with their groundbreaking missions to Jupiter, Saturn, Uranus, and Neptune. Even now, 45 years later, they continue their journey into interstellar space. Researchers, including some who were born after the spacecraft were launched, are currently analyzing the data from the Voyagers to solve puzzles both within and beyond our solar system. In many respects, the Voyager probes have become time capsules of their era. They possess about 3 million times less memory than modern cell phones, transmit data at a rate approximately 38,000 times slower than a 5G connection, and each probe is equipped with an 8-track tape recorder for data storage. Despite these limitations, the Voyagers remain at the cutting edge of space exploration. What are they up to now? What will they encounter next? Let's explore. The launch of these remarkable spacecraft was made possible by a rare alignment of the stars, the 4 largest planets in our solar system. This alignment allowed the spacecraft to gain speed from the gravitational pull of each giant planet it passed, as if being tugged along by an invisible rope that, once released, propelled the probe on its trajectory. One challenge was that the alignment only occurred once every 176 years. To take advantage of it, a spacecraft needed to be launched by the mid-1970s while the lineup was still in effect. NASA seized this rare opportunity by launching 2 spacecraft. Voyager 1 and Voyager 2, identical in design, were launched just 15 days apart in the summer of 1977. They've been operating for nearly 45 years, sending data from the outermost regions of the solar system. These spacecraft have traveled farther and lasted longer than any other in history. Based on our current understanding, they have crossed into interstellar space, marking the boundary between the Sun's influence and the rest of the galaxy. They are the first human-made objects to reach interstellar space, and they are expected to hold this distinction for decades to come. This is remarkable considering the missions were initially planned to last just 4 years. The Voyager spacecraft made groundbreaking discoveries 40 years ago, revealing active volcanoes and fractured ice fields on Jupiter's and Saturn's moons, findings that surprised astronomers who had expected these moons to be as cratered and dormant as our own. Voyager 2 also became the first spacecraft to visit Uranus in 1986 and Neptune in 1989. Voyager remains the only spacecraft to have traveled this far into space, surprising physicists with unexpected discoveries from over 12 billion miles away as it pioneers the exploration of interstellar space. However, their extraordinary journey is nearing its end. Over the past 3 years, NASA has turned off heaters and other non-essential systems to conserve the spacecraft's energy, hoping to keep them operational until around 2030. This marks a bittersweet moment for the scientists who have been part of the mission from the start, as they now face the conclusion of a project that has exceeded all expectations. Voyager 1 reached Jupiter 546 days after its launch in March 1979, while Voyager 2, on a different trajectory, arrived in July of that same year. Both spacecraft were equipped with Vidicon cameras that used red, green, and blue filters to produce full-color images. They were designed to be stable platforms, rotating at a rate more than 15 times slower than a clock's hour hand, which minimized any potential visual blur as they traveled through space. The spacecraft began sending back the first images of Jupiter while still 3 to 4 months away, thrilling standing room-only crowds at JPL. The surprise of seeing Io in color was completely unexpected. Before the Voyager missions, scientists assumed all moons in the solar system would be dull and cratered. However, the incredible variety of moonscapes revealed near Jupiter and Saturn defied predictions. The first hint that there might be more to moons than previously thought came when the Voyagers were still about 1 million miles from Jupiter. One of the spacecraft's instruments, the low-energy charged particle detector, picked up some strange signals. It was the Voyager's cameras that uncovered the truth. Io had active volcanoes. Slightly larger than Earth's moon, Io is now known as the most volcanically active body in the solar system. The colorful appearance of Io is due to the material ejected by its volcanoes, which also caused unusual readings on the Voyager's detectors. Pele, the largest of Io's volcanoes, has produced ash plumes 30 times higher than Mount Everest, with an ash field almost the size of France. In total, the Voyager spacecraft took over 33,000 images of Jupiter and its moons. Each photo seemed to bring a new discovery. Jupiter has rings, and Europa, one of Jupiter's 53 named moons, has a cracked icy shell that is believed to be more than 60 miles thick. As the spacecraft left the Jupiter system, they received a powerful gravity assist, a slingshot effect that boosted their speed by a staggering 35,700 miles per hour. This critical push not only propelled them forward, but also enabled them to escape the gravitational grip of the Sun, allowing them to embark on their unprecedented journey toward the unknown reaches of interstellar space. From here, the two Voyagers took divergent paths as they encountered Saturn. Voyager 1, after its final flyby of Jupiter's swirling storms, was directed toward Saturn's enigmatic moon, Titan. As it soared past Titan's thick, orange-hued atmosphere, cloaking its surface in mystery, Voyager 1's trajectory shifted. It veered sharply to the north, away from the familiar plane of the solar system's planets. Before it broke away into the cosmos, the spacecraft passed through Saturn's majestic rings, enduring the barrage of dust particles that pelted its surface, a final chaotic send-off from the planet's outer boundaries. Voyager 2, on the other hand, took a more extended tour of the outer planets, continuing on to explore Uranus and Neptune before it too began its escape into interstellar space. Together, these twin spacecraft, though now millions of miles apart, continue their silent mission, sending back data from beyond the edge of our solar system, a testament to humanity's thirst for discovery. Voyager 2 also revealed that Triton, Neptune's largest moon, is one of the coldest places in the solar system, with a surface temperature of -391 degrees Fahrenheit or -235 degrees Celsius. The spacecraft captured evidence of ice volcanoes on Triton, which eject nitrogen gas and powdered particles 5 miles into the moon's atmosphere. If not for Carl Sagan, a renowned astronomer and member of the Voyager imaging team, the last images ever taken by Voyager 2, capturing Neptune and its moons, would have been the spacecraft's final photos. NASA initially planned to turn off both spacecraft's cameras once the grand tour of the outer planets was complete, as there would be no more targets to photograph, only endless space and distant stars. Despite the mission being extended and renamed the Voyager Interstellar Mission with the hope of reaching interstellar space, Sagan urged NASA to capture one last series of images. On Valentine's Day in 1990, Voyager 1 turned its cameras back toward the inner solar system and took 60 final shots. Among these was the now famous pale blue dot, a photograph of Earth from 3.8 billion miles away, the furthest image of our planet ever taken. In the photo, Earth appears as a faint, barely visible speck, occupying less than a pixel, illuminated by scattered sunlight reflecting off the camera's optics. Today, the Voyagers are so far from Earth that it takes a radio signal, traveling at the speed of light, nearly 22 hours to reach Voyager 1 and just over 18 hours to reach Voyager 2. Every day, they travel 3 to 4 light seconds farther from us. Their only link to Earth is the NASA Deep Space Network, a global trio of tracking stations that maintain constant communication with spacecraft as our planet rotates. As the Voyager spacecraft continue their journey, their signals are becoming fainter due to their increasing distance from Earth. Detecting these weak transmissions is challenging, especially with all the noise generated by radios, televisions, and cell phones on Earth. However, despite their faintness, these signals have reshaped what astronomers expected the Voyagers would find as they entered the interstellar phase of their mission. It's important not to confuse the boundary of the solar system with interstellar space. The Oort cloud, a distant collection of icy objects bound by the sun's gravity, could extend halfway to the nearest star. The Voyagers won't reach the inner edge of the Oort cloud for at least another 300 years. In contrast, interstellar space begins much sooner, where the influence of the solar wind ends. The solar wind is a continuous stream of charged particles, primarily electrons and protons, that flow outward from the sun at speeds exceeding 1,000,000 miles per hour. This outflow, which also carries with it the sun's magnetic field, extends far beyond the planets, shaping the space environment around our solar system. As the solar wind expands, it forms an immense protective bubble known as the heliosphere, which envelops the entire solar system. This heliosphere acts as a shield, deflecting harmful cosmic radiation and interstellar particles that would otherwise bombard the planets. However, the solar wind doesn't extend indefinitely. As it moves farther from the sun, the particles spread out and slow down, encountering the sparse matter that exists between the stars, known as interstellar medium. This medium consists of a mix of gas, dust, and cosmic rays, and its pressure pushes back against the solar wind. At a certain distance, this pressure becomes significant enough to halt the outward flow of solar particles. This interaction creates a transition zone known as the termination shock, where the solar wind slows abruptly and becomes turbulent. Beyond the termination shock lies the heliosheath, a region where the solar wind continues to slow and interact with the interstellar medium. Eventually, at the very outer edge of the heliosphere, the solar wind loses its influence entirely, giving way to the vast expanse of interstellar space. This boundary is called the heliopause, marking the true edge of the solar system's protective bubble and the beginning of the space between stars. The heliopause marks the boundary between our solar system and interstellar space, but before the Voyager missions, its estimated distance varied widely. According to Gurney, some of these estimates were more guesses than actual calculations. One early estimate placed the heliopause as close as Jupiter, but in 1993, Gurney calculated it to be between 116 and 177 astronomical units, with 1 AU being the distance between Earth and the Sun, roughly 93 million miles. Gurney's 1993 estimates turned out to be accurate, though it took around 20 years for one of the Voyagers to finally reach the heliopause. When Voyager 1 crossed the heliopause, it detected a significant increase in plasma density, about 80 times higher, but there was no corresponding change in the magnetic field's direction. This was surprising, as scientists expected the magnetic field to shift once the probe left the Sun's influence and entered interstellar space. Voyager 2 reached the heliopause in November 2018 at the same distance as its twin, 120 AU from Earth, but it also failed to observe any change in the magnetic field. This added to the mystery, as theoretical models suggested that the heliosphere should expand and contract with the Sun's 11-year cycle. At the time Voyager 2 reached the boundary, the solar winds was at its peak, meaning the heliopause should have been further out, but it wasn't. Theorists' models of the interaction between the heliosphere and interstellar space are becoming more complex now that the Voyagers are providing actual field data. The general picture suggests that our Sun moved from a hot, ionized region into a patchy, partially ionized part of the galaxy. This hot zone likely formed from a supernova when an ancient star, or possibly several nearby stars, exploded, heating the surrounding space and stripping electrons from nearby atoms. To visualize this boundary, imagine a seashore where water and waves churn and mix together. In this turbulent region, magnetic fields twist and turn, unlike the smooth magnetic fields typically depicted in theoretical models. The turbulence observed varies depending on the method of observation, but it's far more chaotic than previously thought. The Voyager data show many small-scale fluctuations near the heliopause due to the heliosphere's influence on the interstellar medium, though larger magnetic field changes are minimal. Eventually, it's expected that the spacecraft will leave this turbulent zone behind and encounter the undisturbed interstellar magnetic field. Bidding farewell to these groundbreaking spacecraft is a poignant moment. Watching their journey come to an end is not easy. Currently, Voyager 2 operates with 5 functional instruments, while Voyager 1 has 4. Both spacecraft are powered by a system that converts heat from plutonium's radioactive decay into electricity. As power output decreases by about 4 watts each year, NASA has had to prioritize which systems to maintain. Despite eventually becoming silent, the Voyager's missions will persist. Voyager 1 is projected to pass Proxima Centauri, our closest neighboring star, in about 16,700 years, with Voyager 2 following 3,600 years later. They will continue to orbit the galaxy for millions of years after our Sun is faded and the heliosphere has disappeared, remaining largely intact. While they might send a final signal during their long journey, it won't be a broadcast from Earth. To communicate with potential extraterrestrial beings, the spacecraft carry 2 golden records. Unlike modern media, these records are made of copper coated in gold and encased in aluminum. They contain images and sounds meant to convey a sense of Earth and its inhabitants. The records include 90 minutes of music, featuring works like Bach's Brandenburg Concerto No. 2 and Chuck Berry's Johnny B. Good, as well as images of people, animals, and nature, and sounds such as crickets, rain, and a mother's kiss. Included on the records is a message from then-President Jimmy Carter. "We cast this message into the cosmos," it states. "We hope someday, having solved the problems we face, to join a community of galactic civilizations." This record represents our hope, determination, and our goodwill in a vast and awesome universe. And that's it. Thanks for watching Spaceverse. From Voyager's historic journeys to their silent trek into interstellar space, their legacy reminds us of the endless wonders beyond our reach. For more cosmic content, like, subscribe, and hit the bell. Keep looking up and stay curious.